here and participate in this one-day seminar. As told, I'm Dr. Baneto from Tago, West Africa. First of all, I would like to give thanks to the registrar of this college and also to the head of the department for the opportunity that they gave me to interact with students through this seminar. I would like also to thank the staff members for the welcome. Also, special thank to Dr. K. Tavijangan, who is my guide. Because I started working with him since 2014, and he helped me so much concerning my research work. So I would like to thank him for arrangement for in this seminar and giving me also the opportunity to be here. So, sir, thank you so much. Okay, for your support also. Thank you. So, Tago, I would like just to tell some words about my country before starting the lecture. Tago is a very small country in West Africa. And it is also, let's say, a poor country. It is a poor country. And this morning, I'm very amazing to see a lot of ladies, a lot of girls in this room. That means these ladies are doing studies in science, in physics, in chemistry, and so on. What am I amazed? Because in my country, I don't have this opportunity to see ladies in science, especially in physics field. My university is born or was opened in 1970, and since that day to now, we never got ladies in physics staff members. No lady since 1970 to now. We don't have lady or ladies in the physics staff members, ni in mathematics. Only some ladies in chemistry, in biology and zoology, but mathematics and physics we don't have. But since I arrived on 11 in Tanjua, and we are making conference in several colleges, I saw that many ladies are in physics. And among 8 or 9 colleges that I visit, we have 7 colleges where ladies are the head of department of physics. Here also.
Yeah.
Okay. Yeah. So, okay, congratulations. So I'm very amazing for that. I'm very amazing. In our department of physics, we have 800 students from UG to PG, 800. And for the first year, we have almost 400 students. And among the 400 students, only 15 girls. Only 15 girls we have among 1-5. Yes, 1-5. Okay. Among 400 students, only 15 girls. So you can understand how it is difficult in my country for ladies, for girls to study in physics and mathematics. Then another thing is that in my country, people think that the lady or the girls must stay home, okay, must stay at home to take care of children, take care of the house, and so on. So there is no sufficient support to the ladies to go ahead in studies. But here, I heard that government is giving a lot of support to ladies. For example, free bus transport for ladies. And also, the government is giving some scholarship for ladies to study. So this is a very, very good things that your government is doing for you. And for that, I would like you to clap for your government for this opportunity that you, yeah, because it is a very good opportunity that it's a very high and big support that your government is giving you. And I would like to encourage you to take this opportunity and go ahead in your studies. Okay, you complete your UG studies, PG and PhD also, because you have the opportunities, you have the facilities, you have to go ahead. Okay, so thank you very much. Thank you for your warm welcome also. Thank you. Okay, so I would like to share with you this morning the topic on organic solar cells efficiency and charge collection challenge, transparent conductive oxides as alternative. I'm working on thin film nanomaterials used for photovoltaic applications, used for solar cells applications. I would like also, maybe it is important to mention, my country is a French country. So in my country we speak only French. French is the official language. So I apologize for my broken English if if it's not okay, very good English. So I come from French country, but I try to speak English, to give lecture in English. And also I would like to tell you, as I already said, my country is not a rich country, it's a poor country, and it is very difficult for PhD students to do PhD in our country. So for PhD studies, we have to go abroad. We have to go abroad to undertake a PhD student. For example, me, I did my PhD in France because we didn't have facilities in our country. And also, as you heard from the Gemma, for the post, I did 3 postdocs also outside my country, because no facilities to do research, you have to go abroad. That's why in 2014, I applied for Civil Raman Fellowship. The Civil Raman Fellowship is a program offered by the Indian governments to help the African countries' researchers to come to India and do research and conduct research. And in 2014, I applied for this fellowship program, scholarship program. Then I was selected and I came in India for the first time in 2014. In 2014, so I met Dr. K. Ravichandran since 2014. And also in 2015, I got another fellowship program called Data Fellowship. Data Fellowship. Then I came back in 2015, and I worked also with Dr. K. Ravichandran. And since this time, we stay working together. And as I said, he helped me very much. He helped me too much to increase my profile, because in my own country I don't have facilities to do research. And I would like once again, tell him thank you for your support. Thank you for everything that you have done for me. So that's to tell you that I will show some research work here. A lot of works are not for practitioners, are not done in my country. So I would like to give this information before starting my lecture. Okay, so as you know, the energy security of the world becomes very, very important. And as the depletion of fossil fuel resource is becoming very, very great, and it is said that up to 15 or 20 years, there will be no a resource of fossil fuels like charcoal and so on. So there is a necessary use to go for another source of energy that we call the renewable energy source. As renewable energy source, we have wind energy, solar energy, biomass, and hydroelectric energy. But among all these renewable energy sources, the most promising is the solar energy. Why? As in Africa, or here also in India, we have the sun shining all the day. So the sun is available, almost 60 hours over 24 hours. So it is a very promising alternative to use solar cells, to use photovoltaic solar cells to produce the energy, to produce the electricity. But as you know, nowadays the solar panels that are available in the market are the solar panel or are the panel based on silicon. The solar panels which are available in the comments are the solar cells based in silicon. And as you know, to produce solar cells to silicon, it demands high energy. And this leads, so the manufacturing technologies are very costly using silicon. And this leads to the expensive solar cells. And faced to this problem, we have to look for another materials, another source to convert solar energy into electricity. So it becomes necessary to find new materials for photovoltaic conversion in order to have low-cost solar cells panel. And in this statement, more research are going on to find other materials which can help to develop solar cells with low cost. Before going to these materials, I would like to show you the photovoltaic technologies. Since the solar cells was discovered, we have almost third generation. The first generation solar cells are based in silicon-based solar cells. And then we have monocrystalline silicon solar cells, polycrystalline silicon solar cells, and above silicon solar cell. After this generation, we have the second generation, which is the generation based on thin films, called thin film solar cells. And among these, we have this type also of solar cells. And then, now we are in this generation called third generation or emergent generation, where we have the perovskite solar cells, quantum solar cells, GAS solar cells, DCC solar cells. DCC means dye-satisfied solar cells, and organic solar cells. Among these emergent solar cells, more research are focused on organic solar cells because the organic solar cells offer a multiple advantage. And among this advantage, we can give some solar cells made with organic materials have been the focus of much research as they are lightweight, flexible. Compared to silicon-based solar cells, the organic solar cells can be deposited on flexible substrates. So we can make flexible solar cells, okay, in contrast with the silicon-based solar cells. And also, they are inexpensive, highly tunable, and potentially disposable because organic materials are available. So it is possible to develop solar cells with low cost. And also, manufacturing costs can be reduced for organic solar cells due to their low cost compared to silicon-based materials and the ease of device manufacturing. The organic solar cells can be developed at low temperature compared to silicon-based solar cells, which are developed at high temperature. Because silicon, we have to do the fusion before making the solar cells. So it needs high energy because the solar cells are developed at high temperature. Now, this is some type of solar cells that was developed since before. Here we have one structure called single active layer structure. Here the organic material is a single layer. Is a single active layer. And with this structure, with this type of solar cells, the problem is that the recombination problem is high here. We have recombination because there is no interface to allow charge separation. So as the exciton is generated, it cannot have separation, charge separation. It becomes very difficult. So we move to this step called bilayer junction structure, when we have an electro-acceptor material and electro-donor material. Here, this structure allows to decrease the recombination problem. Here, we have low recombination because here we have interface. Then, when we have the exciton, the charge can be separated to the field that we have it here, due to the electrical field which appear somewhere here. And to improve the charge separation, we move to another type called bulk junction structure. Here we have a mix of donor and acceptor material. Both are mixed here, and this allows to avoid recombination because once the charge are generated, they can be collected by the electrode easily, and this allows to increase the efficiency of the organic solar cells. Now, let's see here how. Thank you. Please, sorry. So here, I'm showing the relation between the relationship between the organic material and the inorganic material, because to understand well how the organic solar cells work, we have to understand what is the structure considering the organic material and what is the analogy between organic and inorganic materials. In inorganic material, we talk about valence band and conduction band. But in the organic material, we have what we call HOMO. HOMO means highest occupied molecular orbital, and LUMO, lowest unoccupied molecular orbital. So HOMO is equivalent to valence band, and LUMO is equivalent to conduction band. So it is important to understand how it works here. And then we have here the donor material, which is considered as the P-type material, and the acceptor material, which is considered as the N-type material. Then, some requirements are necessary to increase the efficiency of the solar cells or to allow the cell to work well. So, some requirements are these. For the acetone generation, we need that the band gap of the organic material must be included between 1.4 electron and 2.2 electron to absorb photon. Then we generate the acetone. And after that, we have to choose the donor material and the acceptor material. In fact, that the difference of energy between the two levels must be higher than acetone energy. Only this will align, only this will lead to the acetone splitting, to the charge separation. If not, we will have charge recombination and the solar cell efficiency will be very low. So this is a very important, this requirement to allow the charge separation at the interface donor and acceptor material. And after that, as the charge are separate, then electron and hole can be collected by the electrode. Now, here I'm showing the principle of organic solar cells. How it works. First, we have the photon absorption, and then when the photon is absorbed by the material, but by the donor material, then it leads to the acetone formation. This is the acetone, which will move towards to the interface between the donor and acceptor material. And at this interface, we'll have acetone situation. Then you have electron and hole will be separate. Okay? And after that, the charge has to be collected by the electrode here. We have charge transport and then charge collection by the electrode here by the cathode. Now the challenge remains here, charge collection, because sometimes due to the potential barrier between the acceptor material and the electrode, charge collection becomes very, very difficult. So it becomes useful to increase here to resolve this problem by introducing some thin films to reduce the potential barrier, because charge collection here becomes very, very difficult and we have charge loss. And to overcome this problem, we propose to put what we call a buffer layer at this point to allow charge collection. And here I'm showing one structure. This is the structure of the organic solar cells. Here, as I told, there is charge collection problem here, because due to the potential barrier, it is difficult for the charge to move from the donor to the photon node to be collected. So we have to put a thin film here, of a material called buffer layer. So we have to put a buffer layer here to reduce the potential barrier and then to facilitate the charge collection. And it is reported that zinc oxide can be easily used as buffer layer to help charge collection at the interface here. And also, it is reported that zinc oxide in nanostructure form has good electrical properties and will also improve the charge collection. So for our work, we are going to to work on zinc oxide thin films, which will be used as a buffer layer. Then here, this is a schematic, this is a graphical charge collection process. Then here, as I told, we have a potential barrier here. When we, to reduce this potential barrier, we have to introduce a thin films called buffer layer, and this thin film must be homogeneous and smooth to avoid charge accumulation, and it will be good to be high transparency, and conductivity also must be high. This to allow the photon to enter into the solar cells, and then to allow also the charge collection. So as buffer layer, we can use thin film of titanium oxide, tin oxide, and zinc oxide. But among the three, it is important that zinc oxide is a versatile material, and also stable. We can improve zinc oxide properties, for example, by doping or by adjusting some deposition parameters. So it is a versatile material. Zinc oxide is a versatile material. Then it is easy to improve its properties, morphological properties, structural properties, and also the electrical properties. For example, by doping, we can increase the electrical properties of zinc oxide thin films. Moreover, now to synthesize here, this graphic is just to show how it's happened when we don't have zinc oxide as buffer layer. Without zinc oxide, we have some depression here, and when we introduce zinc oxide, this allows to have an alignment of the energy level, and this situation helps to increase the charge collection. This is the solar cells that we develop. This is the structure, and zinc oxide is here. We put it here. This is the zinc oxide thin films. Then, as I said, in my lab, we can just deposit the zinc oxide, but to elaborate all the solar cells, I have to move to France. Or sometimes, I develop the solar, then I send it to France for characterization, because in my university we don't have facilities to make the characterization. All that we have, that is just to synthesize materials, but no facilities for characterization. So we have to send the sample to sometimes in France, and it will take 1 or 2 months before getting a result. So you have to wait up to 2 months or sometimes 3 months before getting results. So it is very difficult, okay, to do research in my country. So this is the structure.